Good evening, everyone.
Good evening.
We are rushing tonight. I saw very, very few drawings on papers as I walked around. Does that mean this is a molecule you've seen in homework and you just like remembered? Or do we actually know how to solve this problem?
Can't you just find where adding
So we need to talk about the steps of how we get there. The steps are the most critical part. So today's class we're going to use to wrap up polarity, ionic nomenclature, which we haven't done in class, but we'll do today in class. And those are our two main topics. So today is the last day to make sure if you have questions about polarity, how to find molecular polarity, that you ask them, we get them figured out in class. There's plenty of office hours. You probably just saw my announcement I sent out in Blackboard. If you don't get the notifications, then you have to go to Blackboard to check. But make sure to look there for office hours, and I'm offering to hold additional office hours between now and the exam. But there's a poll that you'll need to take if you want to participate in that. And I have put some times on the weekends and weeknights, so hopefully we'll find times that work. So process-wise, do you all want 1 minute or so to write down how you would find this? Where are we at in this? Can I get a thumbs up, like I know what I'm doing, we're good? Thumb to the side, not so much. Thumbs down, maybe if I saw the molecule I could remember what the polarity was, but that's about it. Alright, we have a mix all over the place. Literally we have a third up, a third down, a third to the side. So why don't we take advantage of the help in the room? Go ahead and take about 2 minutes. What's the first step you have to do to answer a question like this? Draw the Lewis structure. Okay? So go ahead and do that. If you are totally stuck, please flag one of us down. We have Akia, Sarah, Anil, and myself. And we have Kali in the back as well if we run out of help. So please flag one of us down.
Okay. So I drew it, right? And so I thought that's how many electrons. Did I do that right? No, but I got it. I don't understand clear how you figure it out.
See, I keep getting my polar and non-polar. I get ionic because it's over 2.0.
Can't you tell it's polar?
They're both pulling equally.
So the way that she drew it, are there any polar bonds? Where are the polar bonds in space? That's the question. So non-polar means there's a pole means there's plus and then minus 10. So it means there's a difference in electrons. So none is non.
There's a polar bond. There's a polar bond though between the carbon and the
Yeah, that's where I googled it.
If you got a polar bond between one and the second, not the other second, these are polar, but this is bond.
So those two don't.
So then where's that?
So it means it's non-polar.
So what about this one? Yeah.
But you've got those lone pairs.
There's no lone pairs on the carbon.
Oh, carbon.
Anyone else need a time start?
I put that in the polar. I know, I'm looking at it. All right. I put polar because the
What's the real reason?
you find the electron.
Yeah.
Then you gotta find the bond
All right, so let's go ahead and talk through the steps. So I saw that a lot of people were able to get through the first step of drawing the Lewis structure, which is imperative. You have to be able to do that. If you can't draw the Lewis structure, that's a skill you need to make sure. Go set aside some time and practice. So let me draw a Lewis structure. Okay, we have a Lewis structure. What's the next step once we have a Lewis structure? What's that, Kisa? Score. We look at it, and then, big next step. Determine what? Determine, let's be more specific. We can't just go to polarity of the molecule next. What's the step in between? That's how we get the Lewis structure. That's how we figure out how many bonds. We have the Lewis structure, we're completed. Mel? You're saying atoms in the molecule? It's okay. Okay, so that is kind of a hint at what we need to be thinking about. But the immediate next step is, are there any bonds that we consider polar? What does that mean? What's a polar bond? To be more specific, there's a number that people are throwing out. What is that number we're looking for?
1.5 to 1.9.
Electronegativity, let's be more specific. What about electronegativity? There you go. It's about the difference. If you look, and you can only do this between two atoms. You can't do this for an entire molecule. You can't like add up some magical number for the entire molecule. It's not like that. We say that if we have an atom, two atoms, and we look at them as they're bonded. This is only for atoms that share electrons or have electrons between. We say, what is the electronegativity of one? The chlorine in this case. What is the electronegativity of the other? We'll look at the carbon that's bonded to. What's the difference between their electronegativity values? So we look at our Pauling scale of electronegativity values. This is from Linus Pauling, once again, one of the many things he gave us. What's the difference between those two electronegativity values? What's that, Tay? 0.5. Is that polar, yes or no? Yes, that is a polar bond. So we have a polar bond. I'll highlight that. I don't know if you're going to be able to see the difference. Polar. Okay, then let's look at every other atom that's bonded to that same central atom. C to H. Is that a polar bond? No, why?
0.4 difference.
0.4 difference. And here's a tip, because carbon, almost all of chemistry is looking at carbon to carbon bonds, carbon to hydrogen bonds. Those two are always going to be considered nonpolar. Did anyone get to watch the videos I sent out last Thursday or Friday on polarity? So he talks about butter, right? That like you try to wash butter off your hands with water. That's because water is considered very polar, butter is considered very nonpolar, and butter is full of carbon-carbon and carbon-hydrogen bonds. So fats are almost all carbon-carbon and carbon-hydrogen. I don't know if that'll help, but lipids or fats are not polar, and they're all carbon-carbon, carbon-hydrogen. Okay? So we have a nonpolar CH bond. What about this carbon-chlorine? Polar, 0.5 difference in electronegativity. And at the bottom, CH. The next step is I'm going to draw these dipoles that you've probably seen. So we have a dipole that points from the less electronegative to the more electronegative atom. Basically think of it as an arrow. That chlorine is a little bit stronger desire in a bond to pull the electrons shared towards itself. So the electrons are being pulled a little bit closer to the chlorine. That means the carbon sits on this. You see how it kind of looks like a plus on this end of the tail? So it's a little more positive on that end, a little more negative on this end. And the arrow shows us kind of where those electrons are situated. And we do one on the other side. The size of that arrow, what does that tell us? Is there any difference if I had a really big one on one side and a small one on the other? Is that the same thing? What is it telling us?
The degree of polarity.
The degree of polarity, or how big the difference is in electronegativity values. So if I had a fluorine on one side, I would draw an arrow that was twice as big as the other one, because carbon and fluorine are much bigger differences in electronegativity. Okay, so now we have a molecule. There's 2 polar bonds. Step 2. Now that we know that there are polar bonds in the molecule, what do we do? Call it polar and be done, right?
Yeah.
What do we do?
It's time.
If you'd watched some of those videos, you would have seen them talking about the sum of vectors. So the vectors are these arrows. It's saying that electrons are being pulled this way from carbon to chlorine, to the right and to the left as well. And if we draw those, we draw arrow, let's call it A on the right side, B on the left side. We draw arrow A first, and then we say, okay, it would pull the density of electrons this much towards one side. And then we add, on top of that, arrow B. We start where the first one ended, and then we add arrow B. Question is, do we end up somewhere different than where we started, or do we end up exactly where we started?
Exactly where we started.
We end up exactly where we started, because these 2 arrows should be the same length. I kind of messed that up. But they're pulling in equal and opposite directions. So that is the definition of nonpolar, is when either you have no polarity in the molecule at all, or you have polarity, but it's symmetrical, and it ends up canceling out. So then why is this molecule polar?
Because it's not symmetrical.
Because it's not symmetrical. What do you mean? It's symmetrical. It's totally symmetrical. I just drew it. It's symmetrical. Talk to your neighbor for a second. Why is this molecule polar after everything we just discussed? Talk to the people around you. Try to figure out why it is polar.
I have a question. So this, because they're both equal, that cancels the polar.
Yes, in the drawing I have right there. But there's something missing because it is polar. So what am I missing?
It's something to do with your age. He said it has nothing to do with the age.
Yeah, that makes it
Yeah. But like we draw this way.
But it just has to be symmetrical. It doesn't matter which side it's on. All right. I need a 1 or 2 word answer. Why is this an incomplete story? Someone who maybe hasn't spoken yet. I saw a few hands go up, but maybe someone else wants to add to it. What are we missing? What's the term? What's the concept that I ignored in coming to this conclusion that we have a zero sum of all the dipoles? Tony?
I'm watching her with her hand up. She wanted to speak up.
Who? Megan?
No. She had her hand up.
Okay, go ahead, Tay.
Is it electronegativity? Like the
That's what we use to figure out whether it's polar or not. And then what's the big thing we're missing, Mel?
Well, if we like looked at it as an actual structure, because chlorine is pulling hydrogen and carbon, like they're cool with each other. But chlorine's all like, no, I'm gonna pull on carbon because I'm gonna take over the atom, so it wouldn't be symmetrical because the chlorine would be pulling stronger versus the hydrogen.
sounds good.
I'm going to go a different direction with this. I'm not quite... So there's a major concept that we're missing. What's the major concept? Olivia?
No.
Yes?
Covalent, like naming it a covalent bond since it's polar. No.
No? Good try. Chris? What's that?
lone pairs.
There's no lone pairs on the carbon.
Oh, I mean like on the chlorine.
Nope. You guys had a whole lab!
Wait, what?
You literally spent like a week in lab dealing with this. Come on, help me out. Does carbon look like this? Is it a cross? What's wrong with that? That's 90 degrees difference between the different groups of electrons. Is that as far away as they can get from each other? How far can they get? 109.5 degrees. So that is not what it looks like. It is a what shape? Tetrahedron. Okay, I don't know what happened to this molecule, but this was supposed to be a tetrahedron. It's kind of jacked up with these, I don't know what's going on. But so what should have struck you at first is, well, why did I put the chlorine up at the top and one to the side? It's the same thing, right? It depends on whether, let's say the chlorines are these two balls that we have on here. Do I put it like this, or do I put it like that? Right? You can see that you end up with the chlorines. So here's where the chlorine is up and to the side. Here's where the chlorine is up and down. You can move it however you want. Three-dimensional space, it doesn't matter. So now if we think about the vectors, one vector is pulling this direction. One vector is pulling this direction. Are they equal in opposite directions? So there's a little bit more negative here and here. A little more positive here. So that adds up to not where we started. So you guys need to remember what we do in lab and apply that to class.
So what would our sentence be? So you were asking why is it...
So what is the one missing phrase? It's molecular shape.
So basically what you just said, those arrows right there, forget those.
So if we drew this in 3 dimensions...
But I thought a tetrahedral can also be nonpolar. How does the molecular... Oh, just because...
Okay, so I'm going to draw it in 3D with... So this means the hydrogen is sticking back into the page from the carbon. The chlorine is sticking out of the page towards us. So, and then if we wanted to draw our two vectors, one is this direction, one is that direction. And if you add those up, you're going to end up with something that points, maybe I'll try blue, something that points kind of in that direction between the two. That is not equaling out to 0. Lena?
Why didn't we put vectors on the hydrogen?
There are, so if we say a bond is considered nonpolar, we don't draw the vectors. So anything that is considered nonpolar, that's why it's really important to go around, look at each pair of atoms, C to H, polar or not. If it's not polar, you don't consider it at all in the rest of your calculus. If it is polar, you say, okay, I'm going to pay attention to that one going forward.
So if all 4 bonds were with the exact same atom instead of with hydrogen, could it be nonpolar?
Great question. So let's erase that net dipole. I'm going to do CCl4. Let me change that to green. So if I have 4 chlorines, I want you all, I'm going to do a new clicker question, so I'm going to close this out. The clicker question is this molecule polar or not? I'm going to, hold on, don't change your answers yet. I need to stop. New question. Okay. So the question is this molecule I've drawn on the far right side, CCl4, is that polar, yes or no? And then explain to your neighbor why you answered the way you did.
Same question we
Is A and B
So the question, the options are the same, but we're asking it for this molecule in the square instead. Did anyone forget to bring their electronegativity table to once one? Carmen, you have a question or you want this? Okay, closing out. So we have a split. Someone share their answer and their process. Why did you decide to answer the way you did? Tara.
I could be wrong. But, so I broke it down the way you did on the first one with the C and the CL, and it's 0.5. Well, they're all that way. And that the 0.5...
So what is 0.5? Let's be really specific.
The difference in electronegativity.
Great.
Negativity between the two.
Which means that they are...
Polar.
Great. So all 4 bonds are polar. And then what do you say? What did you do next? So did you decide then the molecule is polar because all the bonds are polar?
Yes.
Okay? That's one of the two answers that was chosen. Did anyone want to argue that? Does anyone want to counter that? Carmen?
I assumed that it all canceled out, like,
Why?
because they're the same.
Okay. Pushing.
They're pushing.
Okay, so remember the shaped tetrahedron, the reason that this bizarre shape forms is because this is equally spacing out all four of the electron domains as far as they can get away from each other. Which means that they're all in equal and opposite directions, if you kind of will. So that means that if all four of these are polar, they're all dipoles, then they're by definition going to cancel each other out because they're pointing in as far away from each other as they can get. So that molecule, going back to the question that was asked, is a nonpolar compound. So carbon tetrachloride is nonpolar. Dichloromethane, which is the first molecule, is polar. All right. So in this question, I did add in here, is the molecule ionic? Is it an ionic compound? What is a dead giveaway that something is an ionic compound? The what is? I will repeat what Taylor said and highly disagree with it. She said the electronegativity is greater than 2. And then we're going to add one word to that that's really important. That's the difference in electronegativity is greater than 2. So if we have a highly polar bond, we call that ionic. But so yes, that's true, but you're not going to go to this and be like, oh, I see the calculation is greater than 2. What is a simple way? What is a really fast way we can tell that there's an ionic bond in the compound? Shelby?
Is it like a metal bond with a non-metal?
A metal bonds with a non-metal. That is absolutely true. Why is that? How does it get us quickly to what Tay and Megan and Tara were saying? What's special about metals and non-metals? Donald? Exactly. The ones that are highly electronegative, the ones that are really high up, they're over here. Remember this red line? This separates non-metals from metals. So basically we're saying, if you see two things that are on other sides of the periodic table from each other, they're going to have a big difference in electronegativity. It's probably going to be over a 1.9 electronegativity difference, and hence it's going to be an ionic bond. So always look for a metal and non-metal. That's half the answer. What's the other half? I'll give you a hint. It's on the other side of this table.
Oh, we already have it.
Does it have anything to do with electropositivity?
Nope. But I like your ideas.
Fair guess.
So what's
What type of
on the other side of the table? Sandra? Say again? By definition, a polyatomic, multiple atoms, ion has an ion in it. So one of the reasons in chemistry we're really excited about, forceful about, requiring you to memorize polyatomic ions, is because if you see a clump of atoms together, you're going to see them really frequently, you have to know that that's an ion.
So that's iron.
So if you see SO4, 2 minus, you know it's an ion, right? But if you see Na2SO4, it doesn't say it's an ion on it. You have to know that that cluster of atoms, the SO4, is going to be found as an ion. So you have to come up with recognition skills to recognize all 15 of these polyatomic ions. Whenever hidden inside of a compound, you see one of these, you should immediately know, oh, that's a -1 charge. That's a -2 charge with that cluster of atoms together. So we'll do some practice with that in our naming. But those are the two most important things. One, memorize your polyatomic ions, because they're going to be on the test next Wednesday, but because they will help you recognize when you see ions. That is one of the things you cannot put on your note card next week. Polyatomic ions. You will be tested on that list of polyatomic ions that I handed out last Wednesday.
Maybe just 5 polyatomic ions.
You will not be tested on all of them, but you don't know which ones I will test you on. So I advise that you learn all of them.
You're going to have a test on
Our next test is next Wednesday, a week from this Wednesday.
We need to memorize the names of them and the charge. Because
Name, charge, formula, and here's the biggest suggestion I can give you. Learn how to draw the Lewis structures for each one. Because I will most likely, guaranteed, ask you to draw the Lewis structure of a polyatomic ion on the exam. Okay? So you will have to know the structure. You will then have to draw the Lewis structure appropriately. And then you'll have to say, in order to form a neutral salt, it needs this many of the whatever other ion it is to form a neutral salt. So, calcium nitrate. What's the formula? Draw the Lewis structure of nitrate. Some chlorate. Some ammonium chlorate. So those kinds of things. So we'll do some practice with that today. So let's get rolling on that. Before we do, we're going to spend a little bit more time with polarity. I want you to be able to look at any atom in a large molecule and do what we just did. In that last molecule, I could only have said, around that carbon, is it polar, yes or no? But remember the big molecule, Abilify? We could have picked any atom and said, okay, what's around this? Does it have any dipoles? If it does, do they cancel out? In order to do that, we need to know what the molecular shape is, and electron geometry, and then figure out there's polar bonds and go through the steps.
In the test, will we have the electronegativity?
I will give you the electronegativity chart on the exam. So if you need to, you can calculate things. However, I advise you look for trends, like we just said, metal, non-metal, or look for polyatomic ions. That will save you a lot of time. All right. I want you also, this is what we're talking about, determine the formula for a neutral salt. And then draw the Lewis structure for and accurately name the 15 polyatomic ions that are on that table. I believe your labs this week are also going to have you working on naming, so they're in synergy in the next week. I also want to let you know that I have heard concerns about lab, and I want to let you know what we're doing to address them. The concerns about lab, honestly, the worst concern that I heard is it feels like lab is set up to make us fail. And that is the absolute last thing that I would ever want for any part of my course. So what I'm trying to do is take feedback from students to try to figure out how to make that not feel like what's happening. I've taken some steps, but I'm also open to other suggestions. So outside of class, if you want to send me an email, if you want to follow up with me somehow, if you have ideas of how to make sure that we're still preparing students for lab, but making it feel less punitive, after you've seen what I'm going to suggest, then let me know, because I am open to trying to maximize success for everyone in this class, okay? So the changes that I'm going to, that we have implemented, they're really all based around this idea, the same as a pre-class quiz. You can't come into lab and have done zero preparation. It just will not work. Just like you can't come into class with zero preparation, you're going to feel lost and it's going to slow everyone down. So we still have to maintain that. So how are we going to do that? The pre-class quizzes, pre-lab quizzes is what they were called before. They weren't a quiz. They were never meant to be a quiz, and so the name was stupid. So one of the things, it sounds really dumb, but it is a pre-lab assignment. It is, here's some things we want that will get you up to speed, and that assignment is worth 20% of your lab grade. So one, it's not a huge part of your lab grade. It is there, it is substantial, but it is not an overwhelming part. So I want you to think of it as lab prep. So get as much as you can on that. You have multiple attempts. If you get stuck, post to Blackboard in my class. I'll create an extra forum where you can post questions there and I'll reply to them. Or you can email your TA. You can, if you get a chance to go ahead of time, post as much as you can as soon as you can.
So is it still going to be 2 attempts?
You still have 2 attempts, yes. So that means that if you go through all the preparatory material, you don't feel like you're able, or you weren't able to get everything in the first try, that's when I want you to post questions and try to figure out how to get there, okay? The second thing I want you considering is that originally the pre-lab component was, in previous semesters, it was worth 30 to 40% of your grade. And this year we actually did make it 20%. And the way that we did that is we also introduced workshop. Workshop is also meant to help prepare you or review things. Your grade for workshop is for completion. It's for participation. And so essentially that 20% of your lab grade comes from participating, being there, and engaging. So when we're thinking about your 40% of the grade before that used to come from pre-lab quizzes, and it was literally a quiz. It was you would go to lab, you would have a lecture from your TA for the first 50 minutes, and then you would take a quiz. And so we're changing that. We did change that so that now you're getting credit for participating in this. And so essentially it's diluted out. So that's things that we haven't really changed. We are considering the technical difficulties throughout the semester that have come with LabFlow, and we are looking at the end of the semester. We are going to do some sort of modification that has yet to be determined that will help make this fair. What we're going to do by the end of this week is upload your workshop grade into the lab grade. I know a lot of people are concerned because their lab grade looks lower than they think they are capable of earning. And so this will help bring it to a point where it is probably more in line with what you think. But it's not going to wipe out anything that's been done in the past. I still do think that there's a lot of value in preparing for lab. And we're trying to figure out a balance between this. So by the end of this week, you should be able to look at your lab Blackboard site. You should be able to see a grade that reflects your workshop and that reflects your lab materials. And then I will take that and import it into our course site so you know how it actually impacts your course grade. So basically what I'm saying is if we zoom out and we take everything in context, I don't think it's as detrimental as it might seem. And I want us going into future labs with the idea of that this is preparatory work. It is not a summative. It is not a punitive. You didn't get it now. And hopefully that'll help with some of the mindset moving forward. Other very brief comments?
It's kind of about, so does lab average into the chemistry course as
It's
a whole?
25% of the entire chemistry grade. So lab is not a standalone credit. It is one of 4 credits. So if you have a 70 in class and a higher grade in lab, it'll modify that slightly. If it's a lower grade, it'll modify that slightly. So you will see that. That's what I'm saying. By the end of the week, I will take your lab grade, put that as 25% of your course grade, and you will see that in Blackboard.
Is each test 25% or how many?
Each test is like 12 or 13% of your grade for the class. Yeah, so in essence, if 2 of your exam grades is worth the same as your lab grade. But if your final exam, if you, like we said before, if you stumble during earlier parts of the semester on exam 1 or exam 2, but you do really well in the final exam, it will replace your lowest exam score. So there are opportunities for recouping if you have stumbled there. All right, so any follow-ups, I do want to hear them. I am listening. We have to figure out how to both help you be prepared, but not feel like you're being overly penalized if you have not been able to get to the point where you need to be at the end of the lab. So I want you thinking about those pre-lab assignments as preparatory work, not penalizing you. So the word quiz means I can't talk to other people. That's not at all what we mean. Okay. Any other questions before I move on? Okay. I put a summary up in our slides for Vesper, how to approach things. We're not going to spend any time on it, but if you want to look at this, hopefully it'll help clarify some of the things we're working on. So let's revisit how to determine if a molecule is polar, because that's one of the things that was introduced in lab, and I want us thinking about how to do that, and we're going to assess you on that next week in the exam. So step number 1 is always, are there any polar bonds in the molecule? So let's do a couple clicker questions here. Go ahead and click in, are there any polar bonds in this molecule? do 10 more seconds. Closing out. All right, so what are we looking for here? How are we trying to answer whether there are any polar bonds in this molecule? Dylan, you want to share your process?
I learned it from him.
Okay, what's the process?
It's symmetrical, nonpolar, asymmetrical, polar.
So you're talking about the entire molecule, and that's not what we're getting at. First step, step number 1, bonds. Are there any polar bonds? What are we looking for? Kaya? The difference in electronegativity between each of the atoms that are bonded around the central atom. Is there a difference in electronegativity between C and H? Yes, but it is in the nonpolar range, so we're going to say pretty much no. Are there any other bonds in the molecule? Okay, so if I asked you, is this a polar molecule, we're done. No more steps. Because the question of polarity is there a non-zero sum? So if we add up all the dipoles, is it symmetrical or not? If we don't have any dipoles, then we're done. So nonpolar. So no, doesn't contain any polar bonds. So the answer directly is not polar. Simple. Gets a little more complicated when we look at some other structures. So let's go ahead and answer that question for this molecule. Are there any polar bonds in this molecule? Five or 10 more seconds. All right, closing out. So once again, following the exact same trend, we're going to say, in this molecule, is there any bond that has a difference in electronegativity? Yes or no? Yes. And if we want to draw where the more electronegative atoms are, this bond, oxygen, is more electronegative, so we draw this dipole that points to the right. That means the charge is a little bit more distributed out here of these 4 electrons. So that means we have to go to second step. We can't stop right there and say it's either polar or nonpolar. Next step is it a non-uniform distribution of electrons? What do we think?
It's uniform.
I mean, look at uniform.
So talk to your neighbor. Decide if this is uniform or non-uniform. Is it symmetrical or is it not symmetrical?
So the arrows, is that what you're talking about, the dipoles?
Yep.
That's what that is. Okay.
Okay. So can I get a volunteer to share their group's discussion? Do we think that this is symmetrical or non-symmetrical, uniform or non-uniform distribution of electrons? Julia, what did you guys discuss?
We said that it is uniform and symmetrical because it's linear.
Okay, what's linear?
The molecular shape.
Okay, does everyone agree? What did we have to make sure was not hiding to say that? What would have changed that answer? If we'd had a lone pair in the central atom that just happened to not be drawn in, either because we were lazy or it just wasn't drawn, would that still be linear? And then we would have a totally different story because we have the 2 dipoles pointing not in a line from each other. So this molecule, if you look at the electron distribution, it is even. It's spread out, so the carbon is a little bit positive. Does that mean that we have a plus on carbon and minus on each of the oxygens? Does that look right? Hopefully that looks really wrong. What kind of a compound would this be if we had pluses and minuses? So ionic means that you have a full positive and full negative And that is not the case. The reason we draw these little arrows is to say, well, the electrons are pulled a little bit further this way. And the bigger that arrow is, the more they're pulled to that direction. So the way that we denote that is either by the arrows, like we have up top, or the other way is to say, well, it's a little bit negative and a little bit positive on this end of that bond. These symbols, it's a Greek delta, lowercase delta, and that means a little bit. And a lot of times it can be like 0.1 of a charge or something like that. And so on this bond we have the same thing, a delta minus on that end and a delta plus on that end. So these say the same thing at the top. So the arrow with the plus tail says that this is the more positive end of the bond. And that's the same thing as down here, showing a little bit positive on one side, a little bit negative on the other side. If you go in and you draw a plus and a minus, I will be very sad. Because that means that it's an ionic bond, which means electronegativity difference is greater than 1.9 or 2. So if you had two atoms that do have a big electronegativity difference, go for it. It's an ionic bond. Draw a plus and a minus. But if not, choose one of these two symbols instead. Either the deltas or the arrow. All right, so let's not use water as an example because it's really lame. Let's go through, what problem is this? Question number 2, 3, 4? Question number 5. All right, we're going to do question number 5. I'm going to show you a whole bunch of molecules, and I'm going to have you go through the steps we just talked about, and you're going to determine whether that molecule is polar or not. Ready? All right, first molecule is HCl. You have 5 molecules we're going to go through. So if you finish one, start working on the next. So HCl, figure out how to determine if that's a polar molecule.
Like that.
Let's take another 20 or 30 seconds on the molecule HCl and click in your answer for that. And if you finish, then start working on BF3. All right, we need a few more clicks. Couple more seconds. If you haven't submitted one, submit an answer. Okay. So we have a pretty strong majority on this one. So what are the steps we would do? Draw a Lewis structure. Once we have a Lewis structure, are there any polar bonds in the molecule? We look for electronegativity difference. We find that there is a difference. What is it, 0.9? So then we say, yes, there is a dipole. In this case, for some reason, this particular animation has it in the bond. So you can see each dipole. Does it cancel out with anything else? There is only one dipole, so that's a polar molecule. All right, go ahead and follow the same process for BF3.
So the arrow is supposed to be pointed like hydrogen?
It's pointed towards the more electronegative element, and that's why you have the little cross on the more electropositive side. Because we have 2.1, 3.0 for electronegativity values. So this one has a greater pull on the electrons. We point it in the direction of the pull. Raise your hand if you get stuck. We got plenty of people to help. All right, we have 33 responses. Do another 30 seconds. Remind you, once you finish that, make sure to do the other 3 molecules. All right, so we have an interesting split, and I think it's not for the normal reason. So first of all, drawing the Lewis structure. Is this a normal Lewis structure?
No.
Why is this not a normal Lewis structure? So boron is one of the exceptions to the octet rule. How many bonds, or how many electrons can boron get away with having? How many electrons?
As many as it wants.
No, not as many as it wants. Boron can get away with having only 6 electrons around it, which is 3 bonds. Instead of the octet, boron is one of the exceptions that can get away with 6 electrons around it. So the Lewis structure for boron trifluoride is shown here. I saw a lot of people drawing this, but then drawing it in a T formation, or not drawing it completely symmetrical like this. Does that matter? When you're doing the next step of figuring out other polar bonds, and if so, they cancel each other out, that's really important. So BF3 looks like this. What's the molecular shape? Trigonal planar. All right, that's stuff that needs to be coming pretty quick now off your tongue. So, are there any polar bonds? So here's, I think, where the confusion came in. What's the difference in electronegativity between D and F? 2.0. So what do we call that? Is that polar or not? It is so polar that it's verging on ionic. Okay? So if you say it's not polar, you're implying that the difference is almost 0. You cannot say that this is not polar. You could say it's so polar, it's almost ionic. So we have 3 really big dipoles to the point where you'd be like, well, they're kind of ionic bonds. This is a molecule that actually does not form ionic bonds, and that's for reasons kind of beyond this class. But part of that is that fluorine is a very small atom, so it's actually closer together. And so those bonds being a little bit shorter makes it just an extremely polar bond. So with that, the question is, do we have dipoles that add up to 0, or do they add up to something else? So these dipoles all add up, and this molecule is considered nonpolar. If we add up those vectors, let's say we do the up arrow first, and then we do the second one. See which ones I'm doing? I'm doing the first vector, and then I add the second vector where that one stopped. And then I add the third vector, and we end up right where we started. All those dipoles cancel each other out. All right. Let's pick up the pace a little bit on these. Go ahead and do NH3. Polar or non-polar? All right, we're at 40. So what do y'all think? All right, I've drawn NH3. Are there polar bonds, yes or no? Yes. N and H have a difference in electronegativity that's big enough to be polar. But, just like BF3, they're symmetrical, right? So it's nonpolar.
No.
Tell me I'm wrong, Lena? Okay, why am I wrong? Because I didn't count up my electrons beforehand. So there's a lone pair, and if we forget about that, if we just look at the formula, these two look identical in formula. So of course they're going to be the same. That's why the Lewis structure is so important. We need to account for all the electrons that we have in the molecule. So if we do a better representation, we would draw it with the lone pair sitting on top of the nitrogen. It's a tetrahedral electron pair geometry, but the molecular shape is trigonal and pyramidal. So all those dipoles, nitrogen is more electronegative. It's pulling the electron density towards itself. So that means that we have a polar molecule. We were mostly on the same page for that one. Carbon tetrachloride. Do we need to go through the entire process for this one? We did this one at the beginning of class. Go ahead and click in your response, but I want you to be able to explain why you're answering the way you are. Couple more seconds. I'm seeing a split in our answer, which kind of scares me because this was one of the first two that we did. Go back and look at your notes if you're not completely clear. Couple more seconds. Check with your neighbor. Still have about 20% of the class that's disagreeing with what we initially found. Make sure you save your neighbor. Save your neighbor. All right, looks like we're not changing anymore. Closing out. Okay, we drew this. It's a tetrahedral molecule. Are there any polar bonds in this molecule? Yes or no? Yes. Every single bond is polar, but they all cancel each other out.
That's what we were sitting here debating.
So that is a nonpolar molecule. So it's not just enough to say, are there polar molecules? Or polar bonds in the molecule. You have to then say, well, where are they compared to each other? Think about that three-dimensional shape. That's the whole reason we did that lab, having you start to visualize what the molecules look like. Last one. I'm going to start a new one. All right. Let's do about 45 more seconds on this one. We'll stop at 1 minute.
second for this?
It's nice that you did that.
And yes, I'm wearing a right mask.
Other people go to work in the hospital and then be sick. I'm like, God, patients here. Yeah, but still you got patients who are like sick. Unless you got coworkers who are spreading stuff. So if you're gonna do emergency, at least wear a mask, you know?
Couple more seconds. We're over a minute.
I got mine. I'm really sure that.
Closing out. All right, our Lewis structure looks exactly like carbon tetrachloride when we had 4 chlorides. But here we have 3 hydrogens and 1 chlorine. So we just pick any one of them. It doesn't matter which one, because remember, it's a molecule. It's in 3 dimensions. We could draw it any way we wanted. Are there any polar bonds in this molecule? Only 1. And what's interesting is that I just saw in your book, it actually does label these H's as slightly positive. For my exams, I do not want you to think about anything that's that 0.4 or less of a difference in electronegativity. I want you to say that we don't even consider it. Really small differences. So if you do go back and read through the book, please do not repeat what it does, because you will, in any chemistry setting, while there is a 0.4 difference between each one of these, we just say that it's nonpolar. So nothing cancels out. That's polar. And we're to the point where a lot of the class is agreeing. The cool thing about this is you can actually take these molecules and you can put them in a magnet and you can measure the magnetic field that exists in some of these molecules. And they call it the dBi is the unit, and that you can calculate the dipole moment. And if you have a really big dipole moment, you can actually measure a significant magnetic field around these molecules. So it's not just something theoretical. Why do we care about this? Why do we care about polar molecules or polar parts of molecules? What's the purpose of this? How they interact with other things. Chris? Okay. So have you heard the phrase like dissolves like? If you get peanut butter on your shirt, or let's say engine oil. If you get engine oil on your shirt, are you going to use water to wash it off? What do you need to use to wash it off?
Detergent.
Soap. Why soap?
That orange.
Fixes everything.
Do you want to see something that hopefully will blow your mind? All right. So we have oil is... Sorry, it's a really bad drawing. How many carbons is that?
Oh, no,
Remember, every one of these is a carbon. Okay, so we have all these carbon atoms. Each one has 4 bonds. If we don't see something, it means there's hydrogens. So that's all non-polar. Carbon, 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 hydrogen. So if we want to wash that out, we can't dissolve it in water because water is polar and that is non-polar. So we can use a detergent. This is half of the detergent. But detergents aren't useful if they're just adding more oil, right? Somehow you have to be able to pour water and have the water pull it away. So what do you need at one end of your soap in order for it to like water? You need oxygen connected to the carbon because it's associated with polar bonds. That sounds silly, but it's super true. So you can have something like this. So whenever you see oxygens in a molecule, you usually think, well, this is probably a polar bond. You can look up the electronegativity difference. This is a polar bond. This is a polar bond. But what makes it even more likely to dissolve in water than the polar bonds? What did I draw? I drew a salt. Remember salts, when you see a non-metal with a metal? Minus, plus, minus, plus. Water has a very strong attraction to anything that's partially charged, or especially a fully charged. So what happens? This tail sticks into the oil. Like dissolves like. It dissolves with it, right? So they are attracted to each other. And then you wash water off, and then this end gets pulled out by the water. Chemistry.
It gets pulled out by the way, what?
So water dissolves this part, but this part's in oil. And so you end up with this phase that this is where you have all the oils are attracted to this end, and on this end you have waters. So when you wash it off, that pulls this into the water, and you actually dissolve the oil in the water. It's these little droplets, and actually the droplets are...
And what happens to the oil then?
Makes the water look bigger.
So in essence, you can think about it like this, where all the fatty parts of the detergent are inside, and the polar parts are on the outside, and then everything around that's water. And it gets these little capsules of oil, and it takes them into the water.
So it just sucks it out.
Sucks it out.
But wait, with those carbon bonds up there, what are the bonds with? There's not hydrogen up there, it's just carbon that's in it.
Well, every carbon has 4 bonds, so that means that that's a CH3.
So
This
when
is 2
all the
hydrogens.
bonds out,
Oh, so they're all bonded to the hydrogens?
Yep. There's all carbons. We only have 2 bonds to each carbon, so there'd be 2 hydrogens on each one.
And the hydrogens are the lines? No.
Lines or bonds between the atoms. So, I want you thinking about these 2 molecules. If you looked at these 2 molecules, if you try to dissolve them in water, one of them is going to dissolve much better. It's the ethanol. Why? Talk to your neighbor. Why would the ethanol dissolve much better in water than the ethane?
I'm guessing that's it.
Chad, can you share what you guys talked about?
I said that the oxygen and the hydrogen makes it polar on one end.
Great. So if we were to draw that out, we would have CH3, CH2, OH. So we have one polar O carbon bond, one polar OH bond. That's going to help it dissolve in water. Ethane doesn't have that, and so that molecule is not going to dissolve in water. So if we look at these 2 molecules, we have vinegar or acetic acid on the left, and we have ibuprofen, Advil on the right. Which one of those 2 do you think is going to be more water soluble, and why? And if you think both are going to be equally water soluble, I should have put option C on here as well.
Wait, what is A again?
That molecule. So acetic acid is this molecule. Ibuprofen is the molecule on the right.
Well, we know you can't mix water and acid.
Just go off of chemistry. Go off of your knowledge of what we just talked about.
I think you need, it's gonna be how the honeycomb pictures work.
All right, let's do another 10 or 15 seconds. Pick one and have a good explanation for why you think that might be the one. All right. Closing out. Who wants to explain their answer? What your group talked about and why you chose what you did? Yes.
I might be wrong, but I put acetic acid since it has more oxygen compared to carbon and ibuprofen.
So let's rephrase that a little bit, and I want to think about the bonds the molecule has. So if you rephrase that in terms of bonds, how would you say that?
Less bonds.
So it does have less bonds, but I don't think that's what you're getting at. So can someone help add to that, Chris?
The ibuprofen has like the same like bonds
as like the acetic acid, but also with a whole bunch more of the carbons and hydrogens.
Okay, so when you say ibuprofen has the same bonds as acetic acid, how do we classify those bonds?
It has like the same molecule in there.
Okay, as part of it, right? But what is it we've been focusing on for the last half hour? Polarity. So, going back to what you were saying, I would rephrase what you were saying to when we see oxygen bonded to something else. When we see oxygen in a polar bond, that's what I want to hear. We see polar bond, polar bond, polar bond. So we have 3 polar bonds in acetic acid. How many do we have in ibuprofen? The same exact number. But then what else do we have in ibuprofen that we didn't in acetic acid? We have a ton of nonpolar bonds. So it's like saying if you meet 2 people, or you have 2 friends, right? One of your friends said something really nice, your other friend said something really nice too. Are you going to call them equally good friends, equally nice people?
Yes.
Well, what if the one friend says a ton of crap behind your back and the other doesn't? It's about that ratio, right? It's about which one has a higher proportion of saying really nice things. The other one says nice things about you all the time. That's almost the only thing they say, right? Really polar. And then this one says the same number of nice things, but it also has all this crap that it throws at you as well.
So which person is dissolved better in water?
By far, that friend is going to dissolve way better in water. You don't need to drown that friend. But does that mean that this molecule doesn't dissolve in water?
No.
Have you ever taken this drug?
Yeah.
I take it very frequently because I hurt myself a lot. Ibuprofen. But what could we do to make this molecule more soluble? Make it more polar at this end.
In a dissolvable tablet.
In a dissolvable tablet. So what if we replace that H with a Na? So instead of having a polar bond, we have a superpolar bond. And now we have a full minus and a full plus.
And there it's like a little cake.
So that's one of the formulations of ibuprofen, is they replace the H with an Na, and now we have an ionic bond, so it's more soluble and it dissolves more quickly in our stomachs. All right. We have 7 minutes left of class, and I had about 40 minutes left of stuff to do with y'all. But it seemed like we were struggling a lot with Lewis structures, and so we took our time through that. So I'm not sure how I feel about that. Okay, let's go through, let's spend less than 1 minute for each one of these questions. Okay? We're going back to Abilify. Pull out your worksheet from last class if you don't have it, or you can just look up here on the screen. You should already know from your previous worksheet what the electron geometry and molecular shape is around each of the atoms that I'm pointing out. So with that knowledge, I want you to tell me first this oxygen. Is there a net dipole? What does that mean? If there's a net dipole, what do we call that? A net dipole means the dipoles don't add up to 0. They add up to something besides 0. So is that polar or nonpolar? That's polar. So this is the same way of asking, is that oxygen, is there polarity around that oxygen?
Does that mean there's 2 carbons attached to it? Like what
Correct.
are those pictures making? 2 carbons attached to
There's
the
a carbon here, carbon there. Every single time the line changes directions, there's a carbon.
There's 2 carbons attached to it.
Is it frozen?
Yeah.
It's weird. Come on, Bodie.
The computer says, I'm done.
Here's it's like you're not getting it stopped down.
Right. It's like, give up on it.
Can you see anything? What do you see on your screens?
It's the last one, ibuprofen. Yeah, ibuprofen was mad that you...
Literally nothing happening. Okay, so we're gonna
Talk about it.
say yes, it's polar. No, it's nonpolar. Thumbs up is polar.
Oh, wait, never mind.
Thumbs down is nonpolar. Thumb to the side is I don't know what I'm doing. Polar, nonpolar, not sure.
It's polar. Which way is the polar?
Polar's up. All right, who wants to share why it's polar?
Wait, are you talking about just between the oxygen and carbon?
We're sorry, we moved. That would be confusing.
I thought it was that O we were talking about.
It's the O we're talking about. Let's repole. That oxygen, polar, non-polar, not sure.
Just the oxygen or?
Around this oxygen, is there a net dipole? Is it polar? All right, who wants to share why? Help me out. We got to roll. Donald. So careful, the two lone pairs are distinctly separate steric groups. So they do not combine at all. So what's our steric number around that oxygen? 4. And if we went through the steps, we already did this last class, so the shape is bent. But before we even got into that, we have to say, are there any polar bonds? Yes or no? Yes, there are 2 polar bonds. Oxygen is more electronegative, so we could draw it like that. And then we know it's bent, so we'd say that that adds up to not 0. So the answer is yes, there is a net dipolar. This is a polar oxygen. All right, let's do the same thing for the next one. So that carbon, still not working for me. All right, thumbs up, thumbs down, polar up, non-polar down. Polar up, non-polar down.
What's connected to it? What's the hydrogens that are connected? Like what? How do you know what's on? There's nothing written there.
So what's attached that's not shown?
A carbon.
One hydrogen is attached to that, and then there are
Why is there a double
carbon on either side.
I don't get how there's a double bond on the hydrogen.
There's not, there's a single bond.
Double bond.
So this is non-polar. Why? Why should this have been really quick to answer? Carbon and hydrogen are non-polar, and the other bonds are carbon to carbon, non-polar. Okay? So if you're not comfortable with line structures, we can follow up after class. This nitrogen, polar, non-polar around that nitrogen center in the molecule. Polar, non-polar. Polar, non-polar. What's missing that's not drawn there? The hydrogen's there, it's drawn. It's bonded to it. But we know that nitrogen has 3 bonds in a lone pair. So what's the molecular shape? If these steps are tripping you up, this is exactly what I'm going to be asking on the exam on Wednesday.
It's a parallel.
So it's trigonal pyramidal. Means it has 3 groups of atoms coming off of it, carbon, a hydrogen, and a lone pair on top. Are any of those polar bonds? All 3 are polar bonds, is that right? They're all 3 polar bonds. So yes, that is polar. Okay. We still have 2 minutes, and I'm going to use up all 2 minutes. All right. And my eye clicker is totally frozen. Let's, I'm trying to think of the timing for today. Let's jump. This is a really, really, really good exercise in practice. When I say draw the polyatomic ions, that is one of the things I really value, and that is something I'll put heavy weight on the exam for. So that means you need to know the names, and you need to be able to draw them. So we have the Lewis structure of carbonate in the top. So I want to know if you found carbonate as a neutral salt with sodium, how many sodium ions are you going to find with carbonate? And I can't click this in because my clickers are frozen. So we'll do a finger vote here in a second. So write down what you're thinking. I think this is on the back side. This is question number 10. All right, hold up your fingers for how many sodium ions we would have around carbonate. How many would we have? I have a mix of 1 and 2. Anyone want to defend their answer?
Because the carbonate has a charge of -2.
But
2 minus, I mean. So it'll take 2 of the sodium, which has 1 valence electron each, to become neutral
Okay, so what Chris is getting at is, when I say the word carbonate, I want you to know that that's one carbon, 3 oxygens, and it has 2 electrons more than all the valence electrons.
So that's always a carbonate right there.
That is the definition of carbonate, and that's why when I say that, it's a terminology thing. I need you to be able to know that. Every time we have a sodium, if it's an ion, it's always going to be +1. Why? What group is it in? Sodium. Group 1A. All of those are always going to be a +1 charge. This chart I will not give you on the exam, but search it for trends. Remember, the ones that are in the middle, you're not expected to know if it can have multiple. But on the far ends, you should be able to figure that out. So if I just had these two together, is that going to give me a neutral salt? I need to have a second sodium in order to give me that. So our formula that is neutral is shown like this. So we didn't have time to get into salts. 1, because you guys asked me to push it off last class and talk about polarity. 2, because I think this class is not very comfortable with Lewis structures. Wednesday's class is going to be on balancing of equations, so we might come back, we'll have to come back to some ionic formulas and things for next week. So let's shelve that until then, but you have some practice in lab between now and then.